Hello, it's Ryan. We're going to keep going over forces in this video. We're going to discuss analyzing forces and free body diagrams, which is the tool we'll create in order to help us analyze forces. Anyway, before we continue on, I have a little blurb that I would like to do, and this blurb is on the unit of force. So we always use the SI, the International System of Units, MKS, meter, kilograms, seconds. And the unit for force in this system is the Newton. Guess who that's named after? 1 Newton, we symbolize that with 1 and a capital N, 1 Newton, where 1 Newton is equal to 1 kilogram times meter per second squared. There we go. Kilogram meter per second squared. One thing you could note to yourself, you can always remember this. So this is what a Newton breaks down into. It's the fundamental unit of a Newton. And you can remember that that's what a Newton always is, because a force is always equal to ma. That's Newton's second law, but forces are in newtons, mass is in kilograms, and acceleration is meter per second squared. And so when you multiply them together, of course, you get a kilogram meter per second squared. So anyway, that's the unit we'll use anytime we're working with forces. The American unit for a force is a pound. And in general, there's about 4.41 newtons in a single pound. Okay, I'd like to also give you an interpretation of this unit, because a kilogram meter per second squared doesn't make much sense, but one way that you can think about that, which I think makes more sense, is that 1 Newton is the amount of force. It's the amount of force required required to accelerate 1 kilogram, so 1 standard kilogram, by 1 meter per second in 1 second. So a Newton is the amount of force required to accelerate 1 kilogram of mass by 1 meter per second in 1 second. And that will be the end of our blurb. So it's just a brief introduction to the Newton, which is the unit of force that we'll use throughout the semester. So in this class, and really in pretty much any place that you need to analyze forces, we'll always use the same sort of tool. So that tool that we use, so maybe we should say this, to analyze forces, we will use a diagrammatic tool. And that tool is called a free body diagram. So free body diagrams, or FBDs. A lot of people will say a force body diagram, and that's not what this stands for. An FBD is a free body diagram. And I've kind of broken down how you should always develop your free body diagrams into about 5 steps. So the first step also helps illustrate why we call it a free body diagram. But in order to do this properly, what we do is we free the body from its environment. In other words, we'll just draw the body separate from everything else. So we'll free the body from its environment. I like to note that usually we treat the body as a point mass. Or we could say we approximate the body, but I'm going to say we treat the body as a point mass. So the first step is simply to draw the body. But usually we could just simply draw a dot if you wanted, or some square or something, and that would represent the body. The next step, once we have a drawing of our body, we need to draw and label any external forces acting on the body. And so that would exclude any internal forces, which may sound kind of silly, but those are existent, like the forces that happen in your body that help you keep your shape. If we're looking at external forces on you, we wouldn't worry about some internal forces that keep your stomach the shape that it is, or your head the shape that it is, or whatever. We would look at forces acting on you like normal forces or gravitational forces. Anyway, so step 2 is to draw and label any external forces acting on the body. Three, we want to draw an acceleration vector on our FBD. So we could say draw an acceleration vector on our FBD. And we might note here that the acceleration vector won't be in contact with the body. And we could note then in step 2 that the forces are contacting the body. We'll see this in our picture in the end, but I like to have it all here. Step 4, we need to choose a coordinate system. So I'll say choose and draw a coordinate system. And there's a little bit of a mental checklist for you, or one checklist for you. When you're drawing your coordinate system, you want to choose a system that breaks up the fewest number of vectors. Of forces and acceleration vectors. So all this will kind of come to light when we do an example. Finally, last but not least, once we have this nice picture all set up, we will apply Newton's second law. And I'd like to know, so once we say we'll apply Newton's second law, I'll put period, apply F equals ma in the horizontal and vertical directions independently of each other. So that's our step-by-step process for constructing and using a free body diagram. But we're going to see it in action. So our first example will be in this video, and then we'll do some actual mathematical examples in the next. So this will be more of a conceptual example, but it will be to show a few free body diagrams. So in this example, we'll have a picture that represents what we'll be thinking about. But what I need you to imagine is that we have a table. And on that table sits a pot holder. And on that pot holder will be sitting a pot. So on that pot holder, we will draw a pot. And in that pot, maybe there's some water or something, I don't know. So there we go. So we have a pot, pot holder. Those probably have a different name, but that's okay. And a table. And so I guess I could show the table is sitting. It's got its legs. And that's sitting on some sort of ground for us. So I never promised to be a good artist, but there we have it. And I'm sure you can imagine now what I'm thinking about. What I'd like to do is I'd like to draw an FBD for each of the three bodies in the picture. And so let's work our way kind of from top to bottom. So we're going to draw a free body diagram for the pot. The first step in our free body diagram was to draw the body. So here's the pot. Just so you know, we could draw the pot just as a little dot. And the same thing would be able to be shown, and that's okay. Another thing we're going to do, just for simplicity, and since it's our first picture and FBD that we're working on, is we're going to say that we're going to keep the water and the pot all one body. So we're not going to worry about the water in the pot. It's all one thing. Okay. So what external forces are acting on the pot? I'll wait. Oh, you're right. The weight force. Anything on the surface of the Earth is being interacted with by the Earth via the gravitational force, and we always will approximate that for our class as the weight force of the object. So I'm going to draw the weight force of our pot, and the weight force always comes and acts through the center of mass of the object. So I'm going to draw it right here. That's the weight of the pot. Now I'd like you to notice that if we said, okay, that's it, that's the only force on the pot, then that would have to also indicate that there's an acceleration in the same direction as the net force on the pot. F equals ma. Well, we know from our picture here that the pot is not accelerating toward the ground, so there must be some other external force acting on it, opposing that weight force that's trying to pull it toward the center of the Earth. Well, of course there is. It's sitting on the pot holder. Anytime we have two surfaces interacting like this, they would create a normal force on each other, just like your hand on the desk. So the normal force is always normal to the surface, and in this case, it'd be normal to the bottom surface of the pot. It's going to be going upward. It's going to be opposing the weight force. In other words, it's keeping the pot from going through the pot holder, isn't it? And so we're going to label this normal, P for pot. So this is the normal on the pot holder, and I was careful to try to draw the normal vector the same length as the weight vector because our acceleration in this problem is 0. The pot's just sitting on top of the pot holder. So that is a free body diagram of the pot. Next, we could do a free body diagram of the pot holder. The pot holder is right here. So the forces acting on the pot holder, well, of course, it has a weight. The pot holder has a weight, PH for pot holder. What else is interacting or touching the pot holder? Well, the pot sitting on top of the pot holder is, of course, interacting with the potholder. If we look back at our first FBD, we can see the pot has a weight force, and that weight force is being countered by a normal force on the pot due to the potholder. So we did know, since A was 0, we did know in here that the normal force was equal to the weight force. But what I'm really trying to get you to think about is Newton's third law. For every force, there's an equal but opposite force. If this normal force on the pot is being acted on by the potholder, so we would say that the pot has a normal force acting on it due to the potholder, then we could apply Newton's third law. If the pot has a normal force on it due to the potholder, then the potholder will have a normal force on the potholder due to the pot. This is starting to get a little confusing, but it's only Newton's third law. The point is, if there's a normal force on the pot, then the pot will exert a normal force on the potholder, and I'm going to show that with the same length arrow. This is a normal force on the potholder. A lot of people might have just labeled that as the weight of the potholder, but it's really a normal force because it's this bottom surface of the pot interacting with the top surface of the potholder. Is there anything else touching the potholder? Well, of course, the table. The table's keeping the potholder from accelerating toward the earth, and so the table's exerting a normal force, normal from the table. We know that that thing is sitting there like a house on the side of the road, so it's not accelerating. Then that means that our upward force must end up equaling the sum of our downward forces, or else they wouldn't, or else there would be an acceleration. You could note that this comes from the idea that the sum of the forces is equal to 0 because A is 0, and this is the same. The sum of the forces is equal to 0. Finally, we could do an FBD of our table. Here's our table. The table has a weight. The table will have the normal force from the potholder acting on it. It will be the same length as that one. Normal on the table due to the potholder. And so what's keeping the table from crumbling, from falling into the earth? Well, a normal force from the earth. And really, in my picture, there'd be 4 little normal forces, but we're just going to approximate that as one normal force in our picture. That's a normal force from the ground on the table. And we know that the acceleration is 0 because it's not moving. So the sum of our forces is equal to ma, but a is 0. So we have ng minus nt minus weight equals 0, and that's where the equalities I was talking about came from before. The whole point is, when we analyze external forces, we use these FBDs to help our analysis. So that's kind of a straightforward and one-dimensional case of free body diagrams. If you noticed in all of these, I did make one mistake, and that was I did not do step 2. No, I'm sorry, I did not do step 4. I did not choose a coordinate system, but this was all one-dimensional, which is kind of why I skipped it. If I was being careful, I should have drawn a coordinate system in all of these. You could also do an XY like that if you wanted to do X in a different direction, but this is all one-dimensional, so we didn't have to worry about breaking any vectors up. So that's a crash course in drawing FBDs. The next few videos will contain worked out examples to really solidify these ideas. Good luck.